Okay, so that we have these equations which are dual to these equations. And I think I got that. I think I recorded that. If not, I'll come back and do it. But anyhow, now we're going to do an example where a car starts with a velocity of -3 meters per second, accelerates 2 meters per second squared, and we want to know how long it takes to get 100 meters from its starting point, right? So these equations, which are dual to these, and we could use these two. You get 4 equations, and your My Lab is going to work you through a bunch of examples of this, and aren't due until Monday, so you got time to kind of absorb this and everything else. Okay, so we want to identify, now we notice that these equations are all in terms of the symbols, 6 symbols, x, x naught, v, v naught, a, and t. X naught is your position at x equals 0. V naught is your velocity at t equals 0, sorry. Your velocity at t equals 0, okay? Okay, so we identify what we know about these quantities. Okay, V naught is -3 meters per second because that's your velocity at the start. And we're implicitly assuming that your start is at t equals 0. Doesn't have to be, but that's the easiest assumption in many cases. It accelerates at +2 meters per second squared, so there's your acceleration. And we want to know how long it takes to get 100 meters. Okay, so we choose to let x naught, we can let x naught be anything, but we might as well let it be 0. That doesn't hurt anything. So x naught is 0, v naught is -3 meters per second, a is 2 meters per second squared. What equation up here has v naught, x naught, and a, and also you want to get to 100 meters, okay? Well, let's see. This equation has v, and we don't want to know anything about v. Maybe we do, but the question didn't ask anything about v. Okay. Now, if we wanted to find v, we would need to know acceleration, time, and v naught, right? And we don't know the time when this thing is going to reach 100 meters. So this equation is not going to help us. We don't know v, we don't know t. This equation, on the other hand, has x, which is going to be 100 meters, has a, which is 2 meters per second squared, has t, which we don't know, okay, and has x naught. Well, we can solve this equation for t. It's a quadratic equation in t, because it's got the t squared and the t. So we kind of want to avoid that if we can, okay? But we could do that. Then if we want to know how fast it's going at 100 meters, that might be something relevant. We could plug that t in here, get the velocity. So this equation could be solved for t. Let's look at these 2 equations. I'm not sure those are the 2 you have in your book, but you have 2 equivalent equations. Okay. This one has v naught. Okay, well, we know v naught. We know the acceleration. We know the x and the x naught. So we could find the velocity at the end, right? So this equation can be used because we know v naught, we know a, we know the x we're looking for, we know the x naught. That doesn't tell us how long it takes to get there. But now that we know v, if we solve this equation, we could plug it into this equation and find t. Okay? Because this equation has a and v naught, which we do know. It has v and t, which we don't. Well, we solve this equation for v, and now we can plug it in here and solve for t. Make sense? If we try to use this equation, let's see if that'll help us. Here we got x and x naught. We don't know what v is going to be. We know v naught, but again, they're two variables. Okay? So we're kind of stuck. Now the equations your book gives you, I forget how they format the things, and how they represent the equations. They all come from these two. And I'm pretty sure those are the two that they use. You understand the strategy? The strategy is to identify x, x naught, v, v naught, a, and t, as many of those as you can. And then if you've got enough of them, you go to the equations and figure out everything else. Make sense? Takes a little practice. And they're going to present it a little differently than I do. You know, listen to them. Okay, these guys they know a lot more physics than I do. Mathematics is my first subject. Physics is peripheral. Okay? I know some stuff, but these guys know how to present things. Okay? So there's very good stuff there. I'm not going to repeat what they say. I could. You're going to see it when you see it. That's the fundamental. This comes from the stuff that we've been doing. And I want you to finish up those graphs so you really understand it all. Related to the calculus in a way that we'll make explicit towards the end of the month, I think. And these equations are just the same as these equations, but in a different situation. This thing that I rolled down the tabletop, and of course that wasn't on the video, roll a thread. This thing rolls down the tabletop, it does rotate. So you have a theta, keeps going up, so you can do exactly the same thing we did. Your graph of theta versus t would be up this way if it's rolling from rest down in incline. It would be the way the graph that we saw for the rotating strap, beam, whatever that thing is. If it was given a velocity at the bottom of the incline, it goes up, okay? But it's exactly the same stuff. And the thetas here just correspond to distances along the tabletop. So all this translates to this, or this could be translated to this if you want to know where the thing is in its rotation. Okay? So there it is.